So I'm Patrice Couvert. I'm French. I'm technical product manager at Calais. So it's the beginning of afternoon after the lunch. So I hope that you can stay awake and hear and understand my French accent. So yeah, the purpose of my talk is to expose how the NVMe over Fabric JBOF can be an ideal solution to integrate NVMe SSDs in the next generation of storage systems. Let's start maybe from the beginning and from the problem definitions. In today, a data center, they are using extensively the virtualization. And the goal was to optimize the resource utilization and allocations. So you have the compute node on one side and the storage capacity on the other side. Using this architecture, you can easily deploy an application on this data center by using thousands of VM on the compute node side, and all these thousands of VMs wants to access their storage on the storage side. And as you can deploy many applications like this on the data center, at the end you can have hundreds of thousands of virtual machines executed on the compute node, going all through the aggregate switch to access this centralized storage, causing what is well known the blender effects, meaning at the end it demands high performance on this centralized storage to deliver millions of IOPS of random access that has been mixed together on the aggregate switch. And this is why, in fact, the storage industry has moved to the SSDs to respond to this demand, exploding demand on this million of IOPS in random access modes. So it has been done in two different steps. So the first step was to use the SAS SSDs, bringing a gain of performance 1,000 times better than HDD for this random access. And then the NVMe SSDs has been introduced to exploit the full performances of the flash, because SAS was initially designed for the spinning disk and sequential access, and it was, let's say, after the SSD introduction, it was the bottleneck in the communications. So NVMe bring a gain between 4 and 7 times better performance compared to the SAS HDDs. But the problem of the SAS of the NVMe protocol is that it is using PCI Express connectivity inside the data center. So if you look at the traditional SAS architecture, this SAS architecture was using some good properties, meaning that you can have storage head nodes that can scale with the number of storage services that you need to execute on these head nodes. You can scale the storage capacity independently on the head nodes. So meaning that if you need more capacity, you just have to include more JBOF in the SAS fabric. When you are moving from SAS to NVMe, if you want to keep the same kind of architecture, meaning that you have storage nodes, storage head nodes on one side, and SSDs, JBOF on the other side, you are obliged to use the PCI Express cables, and this is, for example, what Facebook did with Lightning. But this is where the problem is starting. PCI Express, doing this, you can face many issues. The first one is PCI Express has been designed initially to be a CPU-to-peripheral communications. So meaning it's address-based. It's not like Ethernet, where you can define plenty of IP address and connecting plenty of nodes together. It has been primarily defined to connect one CPU to some peripherals. And when you are using a PCI Express as a connectivity inside the rack, in fact, you see the SSDs as some peripherals, and you are very limited to the number of JBOF that you can connect to your storage head nodes. If I take a concrete example, from what I saw, the existing JBOF one existing JBOF can connect up to 6 PCI Express cable. So meaning that you can just connect up to 6 head nodes on this PCI Express JBOF. So that means the second problem is when you want to add some additional capacity, you are obliged to add also these storage head nodes, because this is where this final JBOF are seen. They are seen through this storage head nodes, through an Ethernet fabric on the front-end fabric. And then you are using a PCI Express, let's say, back-end fabric to connect to this JBOF. So if you want to increase storage capacity, you have to add the storage head nodes as well. On the storage head nodes, as I said previously, you are limited by the number of head nodes that you can add. Typically, this JBOF can have only six cables connectivity, meaning that you can just connect 16 head nodes to this JBOF. At the end, combining all these constraints, you are very limited in terms of compute to storage ratio and flexibility when you are designing or architecting a storage system. And this is an issue with the PCI Express. To work around, let's say, these issues, there are other architecture commonly used. The first one on the left, you can use an x86 JBOF, what I call an x86 JBOF, meaning that you want to expose the SSDs in a raw block mode. And for doing this, you are including x86 plus RDMA NIC and net NVMe over fabric connectivity. And you are just using x86 and RNIC just in kind of pass-through mode, meaning that you just using the main CPU to control the RDMA NIC on one side and the SSDs on the other side. The problem of using this architecture, so you have this x86 JBOF below, and you have still the storage head nodes where storage services are executed on top of this diagram. Problem of this is you are using, let's say, a rich and power-hungry x86 just to expose the whole block modes of the SSDs. And doing this, that takes space, so meaning that you have a lower density, and you have high cost and high power just because rich x86 plus its associated system memory as a cost. On the other side, you can use hyperconverge, meaning that you have on each chassis you have a CPU that is executing compute task and storage service task, and in each chassis you have SSDs attached directly to the CPUs. This is fine, but today you are still, let's say, the constraints of a fixed compute to storage ratio. You can't, let's say, scale the number of compute or the number of storage services independently from the SSD capacity. What would be then the ideal solution? The ideal solution is an NVMeoF JBOF, meaning that you have an optimized NVMeoF target controller that combines the functionality of RDMA NIC and the main CPU to control the SSDs in a single board. Doing this, you can build an optimized JBOF system, optimized in cost, optimized in power, and optimized in density. And once you have these basic building blocks, you can build your storage system very easily with a very high flexibility. You can scale the head nodes based on the services. You can scale the storage capacity as required by the applications. You can leverage existing PCI Express JBOF designs, meaning that if you have boards that can connect in PCI Express slots that was previously used by PCI Express cable, you can just reuse your PCI Express JBOF and you transform your NVMeoF JBOF, your PCI Express JBOF in NVMeoF JBOF. You can build high density because you can compose your system with this high density JBOF system with head nodes. And you have a cost and power optimized solutions. And this is exactly what we are proposing here at Calray. If you want to have an overview of what we propose, in fact, this is a target controller. Target controller is basically an RDMA NIC. But instead of using the network processor on these boards as a PCI Express endpoint, we are using this processor in a root complex mode. Meaning now you can combine the function of the RDMA NIC and the CPU. So having the root complex, you can do the SSDs enumeration. As we can have a standard Linux with a standard NVMe driver directly executed on this MPPA processor, we can control directly the SSDs from the RDMA NIC. We can control up to 255 PCI Express endpoint. And again, as we have onboard memory, we have typically up to 4 gigabytes of memory on this board. We can use this memory attached to this processor as a buffer for the transfer between the NVMeoF fabric commands and the remote SSDs. Meaning that we do not require to use specific NVMe SSDs that have to expose a control memory buffer to bufferize, let's say, all this intermediate data involved in the DMA transfer between the RDMA NIC and the SSDs. For sure, also we need to support the SSD hotplug support, but is naturally supported in Linux. We have started first to develop the RoCE v1 and RoCE v2 protocol stack for the RDMA, meaning for providing an NVMeoF connectivity, you need an RDMA protocol. And as we saw at our customer level, a strong push for the RoCE v1 and RoCE v2 first, we have started by this protocol stack. But as we are a fully programmable solution, meaning that this protocol stack is developed in a bare metal, we can develop the iWarp by the next year, providing a universal solutions that can be configured as either in iWarp or in RoCE v1 or RoCE v2 solutions to support the NVMe over Fabric connectivity. Taking benefit of the NVMe over Fabric, you can have this 4 times better performance than SAS. You have the scalability. We can expose typically up to 2048 initiator, 2048 queues that we can connect to up to 2048 initiator cores. And you have a standard Ethernet connectivity inside the rack.
Excuse me.
Yep.
You're saying 248 queue for each, or 248 cores?
In fact, if you connect 1 core per queue, you can connect up to 2048 cores. Yeah.
Thank you.
And okay, in terms of latency, today we can achieve up to 15 microseconds wire-to-wire latency for 4 kilobytes block transfer. Meaning it's a relatively low added latency compared to the average latency that you have on the SSD side. Board management control, you can support inbound or out-of-band board management. That is end-user dependent. You have the high flexibility, high availability architecture, meaning that you can implement a fully redundant path from the Ethernet connectivity up to all the SSDs. And as we have plenty of cores inside this processor, and we are not using all of them for doing the protocol stack, you have some rooms to add your inline user processing, like compression, encryption, dedup, or such kind of storage task that you can do on the fly. If you look at the hardware description, today we are providing two kind of boards. The first one is KTC80. So all these boards are PCI Express form factor. The first one is full height half length, sorry. And it is a 16-lane PCI Express with a 2x 40 gig port. And the second one is a KTC40, which is in a low profile form factor with 2x 40 gig. But as we have only one PCI Express by 8, the sustained throughput is close to the 40 gig one. Bottleneck is a PCI Express. If you look at the performances that you can get using these boards, on KTC40, we can deliver up to 1.6 million IOPS for 67% read, 33% write in random access mode. And for the KTC80, as we have twice the connectivity or sustained throughput, we can support up to 3.2 million IOPS. Meaning, if you look at these figures, that means that we saturate the 40 gig and the 2x 40 gig port on these boards. Now, if you want to have a quick overview of our architecture, meaning on the processors that is used on these boards. So first of all, you have the high-speed interfaces, meaning that we have two Ethernet controllers. Each Ethernet controller is able to have a 1x 40 gig. We have two PCI Express controllers, and both of them can be configured as a root complex or as an endpoint mode. All these interfaces are connected to a large array of processing. We have 256 cores inside the array of processing. And these 256 cores are organized in 16 clusters of 16 cores. And this is typically where we execute the data plane task in a bare metal level. This is a way to achieve the performances close to ASIC, but with the flexibility of a programmable solution. All these interfaces and all these clusters are connected together through an interconnect chip, high bandwidth and low latency, that has some key feature like direct packet to core delivery and direct core to core transfer, or even direct MPPA to MPPA transfer, meaning that you can imagine to have boards where you put two MPPAs on the same board. We have some projects that are doing this. Finally, in the I/O subsystem, we have also 4 I/O quad cores, and this is where we are executing Linux, the control plane, and for the storage application, it's a kind of I/O proxy for controlling the SSDs. So if you look at the typical protocol stack that we deliver today for this KTC use case, on the clusters, you have the, let's say, data plane protocol stack executed. So you have NVMeoF, you have RockV1 or RockV2. And when the packet is coming in, so it is directly dispatched to the clusters and to the cores. They are executing this protocol stack, decapsulating the NVMeoF packets to retrieve the NVMe commands, and it forwards this to the I/O clusters that acts as an I/O proxy. On the I/O clusters, you have the Linux running here with a standard NVMe driver that we have somewhere adapted a little bit. We are using the standard NVMe driver to control directly the SSDs and to control the DMAs in SSDs. On the clusters, you can add your user inline processing like JBOF encryption and compression, like I said previously. On the quad cores, you can also optionally have your inbound management like SAS using a SCSI stack. You can also imagine to put your user control plane if that is required. This solution, so it's a kind of SDK where you can specialize the functionality. So we have libraries available for compression, encryption, deduplication, erasure coding. In fact, inside the array of processing, we have up to 128 crypto accelerators. These are tightly coupled accelerators. Each accelerator is coupled to 2 cores. And this can typically accelerate all the CRC, the AES, the SHA computation. For example, erasure coding, it's using Galois field computation, and we can use this operator to accelerate the erasure coding computation on the clusters. Board management control. As I said previously, you can do your inbound management as we have Linux running on the quad cores. One other topic also that we saw at this SNEA conference is a determinism. When you want to ensure a low latency for the 99.9999% of transactions, meaning that you want to have a bounded tail latency, you want to optimize the scheduling of the read and write operation to the SSDs. And this is something that we can do by specializing the code executing on this target controller. The main benefit is that when you do this on the target side, you can see all the transactions coming from all the initiator. So meaning that you can do better optimization because if you have multiple initiators, you can schedule the transaction on the initiator side, but you have to synchronize between all the initiator. If you do this on the target controller side, it's much easier to do this. So what are the benefits of using this kind of solution for the storage industry? First of all, as I said, you can just reuse your PCI Express JBOF. You remove your PCI Express cable. You plug or adapter cards in your JBOF system because it's just standard PCI Express, and use a standard Ethernet cables. And now your PCI Express JBOF becomes an NVMeoF JBOF without any modifications, and it's a very quick and ready to use solution. Other benefits, as I said, connecting one adapter cards, you can connect up to 2048 initiator cores. If you look at, let's say, PCI Express JBOF, let's say you have a PCI Express JBOF that can connect up to 6 PCI Express cables. These PCI Express cables can be connected to 6 storage head nodes. So meaning if you have a 72 cores dual socket, you can connect up to 6 times 72 initiator cores to your JBOF. Now, if you look at each adapter card that you connect in your JBOF, you can have 6 adapter cards, and each adapter card can connect up to 6 times 2048 initiator cores. So if you compare this in terms of number of chassis, where you have a dual socket of 72 cores, that makes up to 170 initiators. That means that you have no more, let's say, a limit to connect the number of initiator cores to your JBOF. Scale the storage capacity as you want. In fact, again, if you compare PCI Express JBOF and NVMeoF JBOF, you want to increase the storage capacity in PCI Express. We saw that previously. You have to increase, let's say, to add additional storage head nodes with your JBOF. In the NVMeoF solutions, you can just add another NVMeoF JBOF. You connect it to the top of rack switch, and that's it. You have more capacity, and you are not obliged to put more compute nodes. You can do let's say, standard high-availability architecture using this. This is a typical and simplified diagram. So you have a JBOF where you can connect up to two, in this case, two adapter cards. And each adapter card is connected to a switch. And this switch is connected to one single port of one U.2 SSDs. And if you are using U.2 SSDs that expose two ports, one port connected to each switch and connected to each adapter cards, then you have a fully redundant path from the Ethernet connectivity up to the final SSDs. So this is something that is pretty easy to use. You can scale the performance of your JBOF up to the SSD Peak capabilities. So if you look at the diagram on the left, so if you look at what kind of performances can be delivered by a typical 24 SSDs JBOF, you can have up to 15 million IOPS or 48 gigabytes per second. So million IOPS are given in the use case of 67% read and 33% write in random access, and bandwidth is given in sequential access, 100% read, sequential access. So if you connect only two KTC80, you have 64 million IOPS, 6.4 million IOPS, and something like 18 gigabytes per second in total, meaning that this is the connectivity that will be the bottleneck. But if you let's say, decrease the number of SSDs that you attach to each adapter, meaning if you look at the diagram on the right, if you connect only 8 SSDs to 2 adapter cards, then you can have a JBOF that that can deliver up to 15 million IOPS and 48 gigabytes per second, which is the maximum performance that you can get from all these SSDs inside the JBOF. And this is a typical, let's say, diagram. Typical JBOF with six adapter cards exists today. It's not an invention, but it exists physically today. Now, if you remember of the different architecture, if you were using x86 based JBOF, meaning that you for exposing the raw block modes to the rest of the system, if you want to use an x86 plus an RDMA NIC, and if you look at what kind of power, performance, and density you can get, so this is a use case where you are performance optimized. I took the example of Supermicro 24 SSDs. You can have a dual socket, and you can put up to 3 100 gig RDMA NIC inside this system. So meaning at the end, you can have a let's say for the CPU plus NIC function plus DDR subsystem function, you can have a power that is close to 310 watts, and you can have a final performance of 9.4 million IOPS. Now, if you are using an optimized JBOF, where you remove this x86 and its associated DDR system memory, and you are more spaces to put more adapter cards in this system. So meaning that you can put and plug this 6 KTC80 in the system. Finally, you have a power that should be close to 210 watts, and you can have the performance of 15 million IOPS. Finally, you are 32% more power efficient, and you are 60% higher performance. If you look at another use case which is more density optimized, and this is typically what the hyperscale wants to do. If you look at the standard solution available on the market, again, it's a Supermicro server where you can put up to 48 SSDs in a 2U form factor. And if you take the maximum capacity available per SSD, that makes 154 terabyte in a 2U form factor. Again, you have your x86. You have only two time 100 gig NIC, just because you have less space, because you have put more SSDs inside the JBOF. The power of the CPU plus NIC function will be close to 300 watts, and the performances will be close to 6.25 million IOPS. Now, if you look at as a solution, typical solution used in a OCP form factor, you can have up to 240 terabytes in a 2OU, Open Compute Unit form factor, which is very close to the standard U. And you can connect up to 3 KTC80, for example, in this JBOF. And doing this, you can have a power for the CPU plus NIC function that is close to 100 watts, and while delivering 7.5 million IOPS. At the end, you have 20% more performance. You are more power effective by 64%, and you have a greater density, like 58%. Storage, pay as you grow. It's quite a little bit different than what I exposed previously. When you want to add capacity, in fact, you can have two solutions. The first one is to say, okay, I add capacity and I connect my new JBOF in the top of rack switch. But that requires to use additional ports on the Ethernet switch. One functionality that was available in the SAS connectivity was to chain JBOF together when they are attached to the storage nodes, head storage nodes. And this is exactly what we can do, for example, with our cards, because we are using two ports on the same card. We can connect one port for the storage head nodes, and then using the other ports to do the daisy chain, avoiding to use the top of rack switch to increase the storage capacity. We spoke about the hyperconverged architecture, meaning that if you look at this, typical hyperconverged is where you have each chassis, and for each chassis you have an SSDs in each chassis. Then you have a, let's say, fixed compute to storage ratio, like we said previously. And if you want to put more storage capacity, you have to put more compute node as well. And if you want to put more compute nodes somewhere to keep the symmetry of the system, you are obliged to put SSD as well. Now, if you are using NVMeoF JBOF, you can have all connected to the same fabric in a converged Ethernet fabric. You can have the compute nodes and the storage JBOF connected all together through the same fabric. And you can scale the compute and storage independently. And again, you can still reuse the existing PCI Express JBOF design for doing this. So, conclusion, how Calray NVMeoF can benefit to you? In fact, so we deliver the NVMeoF target solutions, and that enables you to remove the x86 system and its associated memory. In terms of performance, if you compare this to the SAS, standard SAS architecture, where you have the full flexibility of composing system with storage capacity and storage head nodes, you can have 4 times better performances than SAS SSD. You have the full flexibility and full scalability. You can scale the number of head nodes independently of the storage capacity. And you have a fast time to market, as you can use standard PCI Express JBOF, reuse them, just removing the PCI Express cable and connecting this NVMeoF target controller inside the PCI Express JBOF. That's it. Any question?